Welcome back to the AICE Chemistry lecture series. Today we're going to do chapter 2, section 4, which is about electronic configuration. So we're going to grab what we learned in sections 1, 2, and 3 of chapter 2, and we are going to put it together to look at electronic configuration and how to do the electron configurations for different elements. So electronic configuration can actually be represented in one of two ways. The first way of doing electron configuration is often called either shorthand notation or 1s notation, which we see here. We're going to essentially, in 1s notation and shorthand notation, going to be using a very linear way of writing the electronic configuration. Now, for those of you who don't remember, the electronic configuration is how, within the quantum mechanical model, we show how many electrons are in each sub-level of the electron configuration of the atom, So how many electrons are in the S sub-level in the first first energy level, how many electrons in the S sub-level in the second energy level, so on and so forth. We're essentially going to be using this notation right here, where we have the number in the front representing the energy level, the letter next to it representing the subshell within that energy level, and then the superscript or exponent on the letter representing how many electrons there are in that sublevel. Now we're always going to fill the subshells or sublevels from lowest to highest in energy. In order to do that, we're going to skip backwards a little bit. We need to remember this diagram that we studied in section 3 that tells us the orders of the sublevels by kind of crossing them out diagonally. If you need help remembering how to use that trick, you can go back and look at the video for section 3. So, we're going to fill the subshells or sublevels from lowest to highest in energy by using that trick that we learned earlier. We're going to use the number in the front to denote the energy level, and we're going to use the superscript to denote the number of electrons in that sublevel. We can do something called the noble gas abbreviation for most electron configurations, where we supplement the existing part of the electron configuration with the noble gas it corresponds to. What this does is that it abbreviates the electron configuration a bit so that we can write it a lot more simply, because once we get to the higher elements that have 50, 60, 70, 80 electrons, it gets really, really long. So again, what this essentially does is if we look here, this is the electron configuration for aluminum, and we should remember this from honors chemistry, but if we look at the electron configuration for aluminum, within the electron configuration from aluminum is the electron configuration of the noble gas that comes prior to aluminum, which would be the neon noble gas. So neon's electron configuration is 1s2, 2s2, 2p6. So instead of writing aluminum's electron configuration the long way, we can simply just use Ne for neon and then write whatever doesn't fit, which is a 3s2, 3p1, which is unique to aluminum. But I'm going to show you a few examples of this in a second. So let's look at some examples that we can do for this. So I'm going to bring this over here. Now, we have here a few different elements that we can look at for the electron configuration. We're going to do the electron configuration first in the shorthand notation, the 1s notation, and then later on in the video we'll look at some other notations. So for example, if we wanted to do magnesium's electron configuration, the very first thing that we will need in order to do magnesium's electron configuration is going to be the number of electrons that magnesium has. So if we go over here to the periodic table, oops, let's put that back. If we go over here to the periodic table, we can see that if we look for magnesium, it's right here, and the number of electrons in a neutral atom of magnesium is 12. We have the atomic number 12, which means 12 protons for magnesium, and in a neutral atom would also mean 12 electrons. So if we go back, And again, notice where magnesium is on the periodic table. We're going to need that it's on the third row, second column. So if we go back, like we said, magnesium has 12 electrons in total. We said it was on the third row, second column. So magnesium is right here. This Mg. And so when we want to do the electron configuration for magnesium, all we have to do is keep into consideration that we have these 12 electrons. And then from there, we can either use the trick that we learned with the periodic table or the other trick that we learned earlier to dictate the order in which the sublevels are going to be filled. So if we look at here, if we go to magnesium, we have 1s, 2s, or sorry, 1s, 2s, 2p, 3s. So the order in which the sublevels for magnesium are going to be filled, since magnesium is right here, we go start at the beginning of the periodic table and we move sideways. So that's 1s is going to be filled first. And because we have two 1s elements, that's 1s2. Then 2s, we go down to the next one. 2s is the next one to get filled. And then so 2s, again, we had 1s2, so that's 10 electrons left over. Next is 2s, and again, we pass through two elements in the 2s block. So that's 2s2, that's another 2 electrons. After 2s in the blocks is 2p, and we pass through all 1, 2, 3, 4, 5, 6 electrons here, 6 elements. So it's going to be 2p6. So my 12 minus 2 here is 10. 12 minus another 2, or sorry, 10 minus another 2 is 8 left. Now we put 6 electrons in there. That's, oops, go back. Erase that. That's 6 electrons that we remove. That's 2 electrons left over. And if you notice, that makes sense because then we have 3s. And magnesium is the second element on the 3s block. Again, the 3 represents the energy level, which here is represented by the period number. So we have 1, 2, 3. S block means that we have this S sublevel. And then 2 because it's a second element there. And then once we put those 2 electrons, minus 2, that's going to give us 0 electrons left. And that's how we know this is the electron configuration of magnesium. That's by using this trick, by using the trick with the periodic table. If we wanted to do this another way, if we wanted to do this by using the other trick, we will simply just do the same thing, but we will say here on the side, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, so on and so forth. Oops. And then we would, and I'm going to erase this, but you'll see that we'll end up with the same, actually I might just do it in a different color. You'll see that we'll end up with the same answer. If we cross out going from top to bottom in a diagonal pattern, we do 1s first. So we have 1s, and then for the 1s, so again, we have 12 electrons in magnesium. If we put 2 electrons in 1s, which is the maximum number of electrons that the S sublevel can hold, we end up with 10 electrons left. If we then go and we do the next one, which is 2s, again, S can hold a maximum of 2 electrons, so we have 8 electrons left, if we do it that way. Then we have 2p. 2p can hold a maximum of 6 electrons, which we had 8 left, minus 6, we have 2 electrons left. And then finally, 3s is the last sublevel because we can fit 2 electrons in the S sublevel. Minus 2 gives us no electrons left. And that's how we know this is the electron configuration for magnesium. Either way you do this, whether you're using this trick to get the order or the trick with the periodic table, you're going to end up with the right answer. So don't worry about which way to do it. It's more about being able to do it. All right. So that's the electron configuration for magnesium. 1s2, 2s2, 2p6, 3s2. Now, if we want to do something like vanadium, I'm going to go ahead and erase here this and this. I'm going to leave the red one here because I think we got the idea. It's the exact same thing. All right. So let's do vanadium instead. And we'll do it in purple here. Again, we'll do it both ways, but so vanadium, if we go back to this periodic table, if we look for vanadium, vanadium is right here. And vanadium has 23 electrons. It is in the, again, this is the first, second, third, fourth energy level, or fourth period. But it is in the D block, and that's going to be important in a little bit. So vanadium is the 5th element in the fourth period, and it has 23 electrons. So we're going to go back here. It is the 5th element, so 1, 2, 3, 4, 5 in the fourth period. So this is vanadium right here. And we said it has 23 electrons. Put 23 electrons here. Now we're going to do this backwards. We're going to do it with the other one first, and then we'll do it with the periodic table. So again, with the other one, we have 1s, 2s, 3s, 4s, 5s, 2p, because remember the p sublevel starts at the second energy level. 2p, 2p, 2p. Oh, what am I doing? Not 2p. Don't make that mistake. 2p, 3p, 4p, 5p. 3d, because the d sublevel starts at the third energy level. 4d, 5d. And then 4f, because the f sublevel starts at the fourth energy level. 5f, so on and so forth. If you needed to the 6th and 7th energy level, you could. There's nothing stopping you. So if we do it this way, we're going to do the 1s sublevel first. And again, the s sublevel has 2 electrons maximum that it can hold. So 23 minus 2, that's 21 electrons left. After 1s, if we keep doing our diagonals, that's 2s. So we have 2s with 2 electrons. Again, s has a maximum of 2. So that's 19 electrons left. Then 2p, which is a maximum of the p sublevels with 6 electrons. And again, you need to know these numbers from the other sections, that the p sublevel can hold a maximum of 6 electrons. So 2p6 minus 6 is going to be 13 electrons left. If I can do my math right, yeah. Then 3s is the next one. 3s, and again, that's a maximum of 2. So minus 2, that's 11 electrons. Then it's 3p. 3p, which can hold a maximum of 6 electrons. So minus 6, this is 5 electrons left. 4s after 3p. So 4s, which can hold 2 electrons maximum. So we have 3 electrons left. And then finally, and this is the part where it gets wonky, notice how we go from 3p to 4s, but then we go back to 3d. You have to remember, the order is not going to necessarily be by energy levels on 1, 2, 3, 4, because some of those energy levels do overlap. And so the 4s sublevel is filled first, but then the 3d comes in after that. 3d. And then we have only 3 electrons left, even though the d can hold a maximum of 10. So this will be 3d3. And that is all of the electrons that we have for vanadium. So we can do vanadium in this manner, or we can do it by using the periodic table. So I'm going to switch colors again here back to red. Actually, let's do green. We can use the periodic table to do vanadium with this trick. Remember, we have the blocks of the periodic table. So the first 2 columns are the s block, including helium over here. The middle 10 columns are the d block. The 6 columns at the end are the s block, not including helium. And the 2 at the bottom are going to be the f block. Now, when we do this, you have to remember that the period for the S and the P blocks are going to be the energy levels. But for the D block, we won't worry about the F block because it doesn't appear in the curriculum. But for the D block, it's the period -1. So when we're over here in vanadium, vanadium is not going to, even though it's in the 4th period, it's not going to end in the 4D sublevel. Instead, it's going to end in the 3D. Why? Again, because for the D block here, the period, the energy level is a period -1. That's only for the D block. All right. So here, even though it's in the 4th period, that's a 30D sublevel. Whereas for the S and P block, the period would be the energy level. So if we wanted to do the electron configuration for vanadium here, we will go from the top. Again, we always start here at the beginning. We go through 1s, and we go through both of these electrons. So 1s2. Oh, let me make that a little neater. So we have 1s2. Then 2s is the next one. Again, we read it like a book, top to bottom, left to right. So 2s, and we go through both of those elements. So 2. 2p, and we go through all 6 of the elements, so 2p6. 3s, and we go through both of those elements, so 3s2. 3p, and we go through all 6 of the elements, so 3p6. 4s, going through both of the elements in the S block, so 4s2. And then finally, we go through into the D block. Now we're in the 4th period, but since we're going into the D block, that's 3D. And vanadium is the 3rd element in that D block. So this is going to be 3D3. And that's the electron configuration for vanadium. You can use either of these two tricks. It doesn't matter which trick you use. They're both going to give you the right answer. All right. So make sure that when you're doing this, you are looking at your elements correctly. You're looking at where in the periodic table it is and remembering the blocks, or that you're using the trick with the crossing diagonally. So let's look at some other examples. I'm going to go back. We'll do chromium and copper later and you'll see why. Actually, there's one more thing I should have mentioned. Whenever it comes to D block elements, and I'm going to erase here the green just so we have only one per element. Whenever we're looking at D block elements, you'll actually see this written in one or two ways. And either of these two ways is valid, and you can use either of these two ways. But when we look at D block elements, sometimes you'll see it written like this, where I go 4s2, 3d3. So we put it in the order that they get filled, and that's the way that I like to do it because it makes more sense. Or sometimes you'll see the electron configurations like vanadium like this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. And you actually see this a lot in the Cambridge exam. So notice how in the mark schemes, notice how I flipped the S and the P and the D, sublevels here. So here I wrote 4s2, 3d3, which again is my preferred way of doing it. And then here it's 3d3, 4s2. Both of these are correct. Either of these will get you full points. They're done for different reasons. The bottom one is done because of ions, which we'll get to later on. The top one is done because that's the order in which they get filled. Both of these are correct because notice, we still, even when we write it backwards, we still do the 3 on the D sublevel and we fill the 4s completely. So the 4s is still being filled first. It's just a matter of the order in which we write them. Again, the top one to me makes more sense, but either of these are correct, and it is worth noting because when you read mark schemes for the AICE exam, you will sometimes see it, and not actually a lot of times see it written the second way. But again, both of these will get you full points. Don't worry about that part. All right, so let's go back to our PowerPoint. So we can look at a bunch of examples here. These are the first 18 elements and their electron configurations on the left side. So these are the full electron configurations. So we can see how going from hydrogen all the way up to argon. You can see how we successively fill 1s, 1n, 1s2, and then once the 1s2 is filled, we go to 2s, and then once the 2s is filled, we go to 2p, and then after 6 electrons, when the 2p is filled, we go to 3s, and once that's filled, to 3p, all the way down to argon. So as we add electrons, all we're doing is just adding more electron sublevels, or energy sublevels, in order to have somewhere to put those electrons. Now on the right side, you'll notice that once we have to 19, these electron configurations are getting really long once you guys have to add the 4s. And so you can see here the electron configurations using that noble gas configuration. The noble gas configurations, again, is really easy because all we're looking for is the last energy level that was completely filled for the S and the P sublevel, and then exchanging that for that noble gas. So we're going to do it in a second, go back and do it for magnesium and vanadium. But notice all we're doing for the abbreviations is that we are including that noble gas prior to the element instead of all of those electron configurations that we have. So if we look at our examples here, so if we go back to our examples, I'm going to erase this second one just so we don't get confused. So all we will have to do here is, if we're looking at our examples, let's start with magnesium. All we will need to do is go into magnesium, look at the very end of this electron configuration, and we're going to look for an S and a P sublevel that have both been completely filled for the same energy level. So here we see that for the third energy level, there's the 3S that's completely filled, but the 3P's in there. On the other hand, for 2p6 and 2s2, here for the second energy level, they have been completely filled. Because the S sublevel is always filled first, realistically speaking, all we have to do is look for this 2p6. So you're going to find the very last p6 in the electron configuration. And then you're going to go to the periodic table. So we're going to go here. And again, let's erase this from before. We're going to go here. So we were working on magnesium. We're going to find the noble gas before magnesium. So not argon, which is the noble gas with magnesium, but the one before, which will be neon. And we're going to put neon instead of every part of the electron configuration that comes before the P6. So again, we find the noble gas before the element we're looking for. We have magnesium, noble gas before that element, so we're going to go up one all the way to the end, is neon. So we're going to go back to our electron configuration. We're going to find in the electron configuration of magnesium that last P6 and everything before it, including the P6, we're going to replace with that noble gas, neon. And then what's left over, that 3s2, we're going to include that into our electron configuration. So neon 3s2, this is the noble gas electron configuration for magnesium. Again, we're finding the very last P6, and it has to be P6, not P2, not P3, P6. Everything before that P6, including the P6, we replace with the noble gas that comes before, because that is the electron configuration for the noble gas. And then we are going to add whatever is left over. And I'm actually going to, so I need this piece later. I'm going to grab this and put it over here. So this is the noble gas electron configuration for that element, for, in this case, magnesium. And you see it's much shorter. If we do the same thing for vanadium, again, we're going to go back and with blue. So I'm working on vanadium now. Oops. So we're going to go find vanadium on the periodic table. So if we find vanadium, which is right here, we're working on this guy right here. If we go up one and all the way to the end, we find argon is the noble gas before vanadium. So it's the same thing. Because argon is the noble gas before vanadium, we're going to find the last P6 in the electron configuration of vanadium. And then we're going to replace it with argon. So again, we go back to the electron configuration. We're going to find the last P6. So working from the back, we have V3. That's not it. S2. That's not it. And then before S2, we see that we have 3 P6. So that's the last P6 in this electron configuration. So we're going to grab everything before that. And we're going to replace it with argon, which was the noble gas before vanadium in parentheses. And then anything that is not included in that, we'd still write. So the 4s2, 3d3, we'll still write as 4s2, 3d3. And that is the noble gas, electron configuration for vanadium. Now, normally on the AICE exam, and this is very important, unless you're asked specifically for the noble gas electron configuration, do not do this. Sometimes it will ask you for the noble gas electron configuration. A lot of the time they do not. So unless they ask you specifically for this, do not do the abbreviation. A lot of the time what they'll give you is they'll give you 1s. Let me read that. A lot of the time what they'll do is that they'll give you something like this. 1s2 and then a line for you to fill in the rest of the electron configuration. Notice that if you have the 1s2, you cannot use noble gas abbreviation. I'll just put abbreviation. You cannot use abbreviation when you see a 1s2 because that 1s2 would normally be part of the abbreviation. So you wouldn't be able to use that noble gas in that electron configuration. So be very aware on the AICE exam what the question is asking you for and how that question is structured. All right, so let's continue here. So again, that's the noble gas abbreviations for some of the elements. Now, copper and chromium. I said we were going to come back to copper and chromium. And copper and chromium are special. And technically speaking, the column for copper and chromium is special. Both the groups that they're in are special. But copper and chromium are our model elements. And then everything from there will kind of follow. Or everything that's in the same group will kind of follow the same example. So in the previous slide, you may have noticed that copper and chromium do not follow the rules for electron configuration. In the case of both copper and chromium, the 4s sublevel or subshell is actually only half filled before moving on to the D sublevel. So you can see here for chromium, we go argon and then 3d5, 4s1. So notice how normally we'll have the 4s be completely filled like we do in scandium, like we do in manganese, like we do in zinc, before moving on to the D sublevel. But for copper and chromium, the 4s is only half filled. It's 4s1, even though we are putting electrons into the D sublevel. And this is the case because it's more stable. Essentially, copper and chromium use a little bit of energy from the environment to move an electron from the S sublevel to the D sublevel. And that's because if you look at it here, if we have 4s1, 3d5, the alternative will be to have 4s2, 3d4. A half-filled and a fully filled sublevel, like we have here with 5 and 10, are always going to be more stable than a partially filled sublevel other than half-filled. So essentially, there's an order to stability. The order to stability that we have for sublevels are like this. Fully filled comes first. So if we have a fully filled energy level, that is the most stable. Then second is going to be half filled. So any sublevel that's only half filled, like a D with the 5 electrons, or a P with 3 electrons, or an S with 1 electron. It's going to be also very stable. And then partially filled is the lowest of the three. So again, this is going to be the order of stability. As we move up, they become more stable. Let me move that. So as we move up, they become more stable. All right. And this is something that you need to remember because it is the explanation for a lot of things in chemistry. For sublevels. So if we look at the electron configurations for, again, chromium and copper, if we were to do them regularly, what we would end up with would be AR 3D4 4s2. So here we have a partially filled sublevel and a fully filled sublevel. For chromium, or sorry, that's for chromium. For copper, we will have AR 3D9 4s2. Again, a partially filled and a fully filled. The fully filled, however, is an S sublevel, which is arguably a lot smaller because there's only 2 electrons, and so it being fully filled is not as stable. In the other hand, what we actually get when we take the exception into account, we get a half-filled sublevel with a D and a half-filled sublevel with the S. In copper, it's even better because we have fully filled D sublevel and a half-filled S sublevel. So because we have no partially filleds here, we have a much more stable electron configuration. So if you're going to gain anything from this, it's just to remember that copper and chromium are exceptions where we only put 1 electron in the S sublevel before moving on to the D sublevel. So again, let's look at that in our examples. I'm going to erase this. If we look at that in our examples, if I can move it, we have here chromium. If we were to do chromium, and chromium is, let me use a different color. So we're going to use chromium, which is, I'll put the periodic table up. So we look at chromium. Let me erase this. So chromium is right next to vanadium. Chromium is right here. If we were to do our chromium electron configuration, we had 24 electrons. So chromium is right here. That's CR. If we were to do this normally following our technique that we learned earlier, we have 1s2, 2s2, 2p6, 3s2, 3p6. Again, we're going through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. This is wrong. This is what you don't want to do. Because, again, this right here, this 3d4 or 4s2, this is the part that's wrong. Because chromium is an exception. And we need to remember that exception. Let me fix that E. So this is going to be wrong. What we're going to do instead, and that you have to remember for chromium, is that we will grab the 4s and only put 1 electron into it. What that allows us to do is that now this 4s is half filled. And then when we do 3D and we put 5 electrons instead of 4, because we still have we still need those 24 electrons. I believe it was 24. Yeah, 24 electrons. We still need those 24 electrons. When we put the 3d5, now we have a half-filled and a half-filled sublevel. Instead of with the wrong confirmation having a fully filled S sublevel and a partially filled D sublevel. This makes chromium a lot more stable. And so this is the actual electron configuration for chromium. with its noble gas electron configuration being AR, and then orange, 4s1, 3d5. So make sure you remember this for when they are asking you to the electron configurations for chromium and copper, that you need to remember those exceptions. And we'll do copper next. So half filled, half filled. Let me move this a little so it's a little more clear. Over here, 24 electrons. So for copper, again, same thing, but copper is now over, let's do say for color. Copper is now over here, Cu. So I'm gonna erase my chromium here. We're gonna go look at copper. So copper is over here, and copper is even more of this kind of exception. We have 29 electrons, and copper is 1 electron shy from having a fully filled d sublevel, which is really stable. So we have 29 electrons in copper. So we're gonna come over here. And again, copper is only 29 electrons, and we need to remember that this is an exception. So when we do copper, again, we're gonna go through this like we would normally, all the way till we get to the last two, 4s and 3d. So we're gonna have 1s2, 2s2, 2p6, 3s2, 3p6. And then once we get there, 6 plus 2 is 8, plus 6 is 14, plus 2 is 16, plus 2 is 18. So minus 18, this is 11 electrons left. And that's where those 11 electrons are where we kind of come into the issue. Because, again, if we did this normally, and this is the wrong thing to do, so don't do this, we will go 4s2, 3d9. And that's our 11 electrons, right? But this is wrong. Why? We have a fully filled S sublevel and a partially filled D sublevel. The D sublevel is a lot bigger than the S sublevel, so we don't want this to be partially filled. And nature doesn't either. So what does nature do? It grabs energy from the environment and moves one of these electrons over from the 4s sublevel to the 3d sublevel, because they're pretty close in energy that nature can do that with just ambient energy from the environment. When that happens, that 4s electron goes into the 3d electron, and this happens naturally, it's always going to be there, so you don't have to show it. 3d now has 10 electrons, and 4s has 1 electron, which means that now the 4s sublevel is half filled, and the 3d sublevel is fully filled. That's a lot more stable than before when we had this fully filled and this partially filled. And that's how the 11 electrons that are left over at the end are organized. 4s1, 3d, 10. So always remember, for chromium and copper, do not do the normal way. Make sure you only put 1 electron in that 4s and then fully fill the 3d for copper, or half fill the 3d for chromium. And again, if we're going to do the noble gas electron configuration here for this, it's going to be argon, and then 4s1, 3d10. And that's our noble gas electron configuration abbreviation for copper. I'm going to erase the... No, let's just do that for now. So this is actually true not just of copper or chromium, but of all of the elements in their columns. I'm going to do one more example here that I didn't have listed just to show you that. So if we go, and we're going to use the electron configuration for this just to make it shorter, so the abbreviation, the noble gas abbreviation, to make it shorter. If we go here, let's say we're doing silver. The abbreviation for silver is going to be very similar for that of chromium. So silver, if we're doing silver here, let's do it in, let's do it in this magenta color. So if we're doing silver, the electron configuration, the abbreviation for silver, before it is going to be krypton. So we're going to use krypton for its abbreviation. And then we have the 5s block here. and then the 4d block for silver. So 4d sublow, 5s sublow are the last two. So we're gonna do it here. Actually, we'll do it right here in the bottom. So we have krypton in brackets, and then we have 5s and then 4d. Again, because silver is the same column of exceptions as copper, and again, for chromium will be the same thing. When we put these electrons in, we're not going to do 5s2 for the 9. We have the same exception we have with copper. So here for silver, the abbreviation is going to be krypton 5s1 for the 10. Because again, this makes silver a much more stable electron configuration than we had before. All right. So this is going to be true not just of the copper, but also of any element in its column. Same thing with chromium. Obviously, once you get low, too low, like with tungsten or gold, then we have to take into consideration the F block, which gets really tricky. So we're not going to get into that. But this is the one for silver, just so you can see how you might be asked to kind of expand and go forward, not just copper and chromium, which is what's in your curriculum, but to do them for similar elements in the same group. Because remember, the elements in the same group have similar properties. So when I do that, I'm going to clean this up a little to leave it ready for what we're going to do later. So give me 1 second. Summarize this, and then I'm going to erase these numbers up here. And again. And how much less of these exceptions and put them somewhere else. Check that out a little better. Come on. Okay, we'll do that later. So let's keep going here. So this is an example of what you might see on the AS exam. This is a very simple question because they're not even asking you to go all the way and write the full electron configuration. They're actually just asking you to complete it. So right now we have on the screen the electron configuration for strontium, it says here. So we have 1s2, 2s2, 2p6, and they're asking us to complete or to finish the electron configuration for strontium. So what we're going to do is, what we need to figure out first is how many electrons does strontium naturally have. And to do that, we're going to need our periodic table. So I'm going to bring that back up. So if we look at strontium here, the electron configuration for strontium, or the number of electrons for strontium, is 38 if strontium is neutral. Because remember, if you have ions, that's going to change the number of electrons. But it's 38 for neutral strontium. So we're going to work off of that, and I'm going to use this one just because it will stay there. So it's going to be 38 electrons. And we're going to move this back out. So we have 38 electrons for strontium. Well, right now here we have 2, 4, and then 6. This is 10 electrons in total. So they've given us 10 electrons already for strontium. So that means that we have 28 electrons left. And so all we have to do is do the same thing that we're doing before, but just finish out the electrons that we have left, the 28. So after 1s2, 2s2, 2p6, after 2p6, if we use that trick that we learned earlier, is 3s. Oops, and let me do this not with a highlighter. So it's going to be 3s after 2p6. So it's 3s, and s has 2 electrons. So we have 26 electrons left. 28 minus 2 is 26. Then after 3s is 3p, and that can have 6 electrons. So 26 minus 6 is 20 electrons left. After 3p is 4s, which has 2 electrons that it can hold. So after 20, it's 18 that we have left. After 4s is 3d, which can hold 10 electrons. So 3d is 18 minus 10. Oops. Minus 10 is going to give me 8 that we have left. After 3d is 3p, or sorry, 4p, should I say, which can hold 6 electrons. So that's going to give me 2 left. And then after 4p is 5s, which can hold a maximum of 2 electrons. And that's all of the electrons that we needed. So the complete full electronic configuration of strontium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. And if we look at the answer, that is exactly what we have. Again, notice how the 4s, and I'm going to highlight them. Notice how the 4s and the 3d are backwards here. So here they have 3d10, 4s2, whereas I have 4s2, 3d10. And that's all right. Either way of writing this is correct. What matters is not necessarily the order between 4s and 3d. Everything else, the order does matter. But between 4s and 3d, what matters is that you have the right exponents, which we do. It doesn't matter whether you flip them or not. Now notice also that we cannot use the abbreviation here because we have that initial part of the electron configuration already written for us. So if we had used the abbreviation, the noble gas abbreviation, we would have gotten points taken off here. All right. So this is just a basics of how we do this. These should be pretty straightforward questions because the skills that we're using here, the electron configuration skills, are skills that we learned in honors chemistry. So make sure that when you are looking at these, you are following all of those very basic skills that you learned. So everything from last year, you can just forget. You do still need to remember them because these are the points that you will get easily on the test. That you will get one, this is 1 mark or 1 point. This is the 1 point you will get easily. So you want to make sure that you got these so you're not then struggling for points later on when the questions get harder. All right. So now the other thing is the other type of notation, which is called box notation. So box notation is essentially a more detailed way of doing the simplified electron configuration that we're just looking at. Now, why is box notation more detailed? Because it involves the orbitals. When we were looking at electron configuration, I'm going to go back for a second. When we were looking at the electron configuration, notice that we do not talk about the orbitals. We have the energy level, which is represented by the number, and the sublevel, which is represented by the letter. What we don't have is the orbitals. So if we look at these charts are essentially how we can do box notation. Box notation follows the same idea. It's still a type of electronic configuration, meaning that it's going to tell us how many electrons there are in each one of the energy levels and each one of the sublevels. But on top of that, it involves having how many electrons are in each orbital. In box notation, we're going to have those sublevels, 1s, 2s, 2p, 3s, 3p, 4s, 3d, in the same order that we did with the electronic configuration with the shorthand or the 1s configuration. But we're going to have either below or above that squares that represent the orbitals. So you'll notice that the 1s, 2s, 3s, and 4s sublevels have 1 square below them because the s sublevel only has 1 orbital. The 2p and the 3p sublevels have 3 squares below them because we have 3 orbitals in the P sublevel. And then the D sublevel, the 3D sublevel, has 5 boxes because we have 5 orbitals in the D sublevel. So we're still going to follow the same general rules. However, we're going to add some rules here. Number 1 is that we, hopefully, as we know from prior sections, an orbital can only hold 2 electrons. So we're going to have the same rule that we had for electron configuration, which is least energy to most energy for the sublevel, so 1s, 2s, 2p, the order. And then we're going to add another rule, that there can only be 2 electrons per orbital, and they have to have opposite spins. This is known as Pauli's exclusion principle. Pauli's exclusion principle says, which we learned in honors chemistry, that we can only have 2 electrons in an orbital, and that those electrons must have opposite spins. Now, we're not going to get into the details of what a spin is because it can be very complex, but just you can think of it as the electron rotating or spinning, and they have to spin in opposite directions. Now, how do we represent an electron in this type of notation? Well, if we're looking at hydrogen, for example, hydrogen only has 1 electron. So how are we going to represent that 1 electron? We're going to, let me make that smaller. We're going to represent that 1 electron as an half arrow. So it's an arrow with only half of the head on the arrow. And it's going to either point up for one spin or point down for the other one. Since hydrogen only has 1 electron, that 1 electron goes into the first orbital, the 1s, and it doesn't really matter whether it's spinning up or spinning down because it's the only electron in there. Now, if we go to sodium, again, sodium has a few more electrons. Sodium has 11 electrons in it. And again, we can see that by bringing up the periodic table. So if I bring up the periodic table, we can see that sodium, a neutral atom of sodium, has 11 electrons. We can see it right here, sodium 11. So that sodium atom is going to have 11 electrons. And those 11 electrons will need to go into the respective boxes. Well, if we fill them in, again, we're going to put 1 electron up and then 1 down in the first box. Because we're still going to fill this in like we would with the electron configuration. We have 1s2, 2s2, 2p6, 3s2. That's the electron configuration for sodium. Sorry, this should be 1 at the end. But now we actually need to not just write a number, but demonstrate how those electrons look. So the 2 electrons in 1s are going to be represented by oppositely spinning electrons, because we can only have oppositely spinning electrons in an orbital, 1 going up, 1 going down with the half arrows. 2s, again, 2 electrons, 1 orbital, so it's 1 going up, 1 going down. Now, for 2p, we have 6 electrons, and they're all filled. So again, each one has 1 going up, 1 going down, because we're going to have only 2 electrons, and they both need to be in opposite directions. When we get to the 3s, when we only have 1 electron, we can put down pointing up or pointing down. That doesn't matter. In this case, I like to put them pointing up, but it wouldn't really matter which way I put them. Now, there is one more rule to this that I should mention. The other rule that we got to look at when we're doing electron configurations is called Hund's rule, but you don't need to know the actual name. But the rule is that orbitals with the same energy get filled with 1 electron each, all of the same spin before completely being filled in. Now, what does that mean? So let's look at, for example, phosphorus, which has, I believe it's 15 electrons. Let's look at the periodic table. So I'm bringing in a different periodic table. If we look at phosphorus here, phosphorus has 15 electrons. So we can see it right there. So we can see that phosphorus has 15 electrons. Well, when we distribute those 15 electrons into the sublevels, we're going to have 1s2. Let me fix this. We have 1s2. Oops. 2s2, 2p6, 3s2, 3p3. That's 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. How do we draw these in? And that's where this is going to become important. So if I draw these electrons in, one trick that you can use in order to kind of do this right every time is going to be, I'll put here 15 electrons, to draw these up down electrons. So anytime we're doing s sublevels, we're going to do one up, one down, one up, one down. And what that's going to keep us from doing is putting two of the same spin in the box. And then when we're doing something like a p or a d sublevel where we have multiple electrons going into what we call degenerate orbitals. And what does that mean? That means that they're all in the same sublevel. So these three orbitals are degenerate. When we fill the electrons into these degenerate orbitals that are all in the same sublevel, we're going to do so by putting one electron in each before we start pairing them up. Because that's what rule number 3 tells us. Orbitals in the same energy, meaning same sublevel, get filled in with one electron each, all of the same spin, before being completely filled. What does that mean? That means that when we do a sublevel with multiple orbitals, that means anything but an s sublevel, we're going to do 1, 2, 3. We're going to give them each one electron, all facing the same way, before we go back and we say 2 or 3, 4, 5, 6. So we're going to put one in each before we start pairing them up. Because all of these orbitals have the same energy, and so the electrons don't pick and choose where they want to go. They have to evenly be distributed. Think about it this way. If you had 3 friends and you had 3 rooms in a vacation home that you went to, will you put 2 friends in one room and 1 friend in another and leave a room empty? Or would you put 1 person per room? Like, it makes sense because of repulsion. It makes sense because you and your friends don't want to be in the same space, and neither do these electrons. So again, when we go to 3s, 1 each way, and we're going to see especially when we do these 3 electrons in the 3p sublevel. When we do the 3 electrons in the 3p sublevel, again, we want to do 1, 2, 3. We want to put 1 in each room or 1 in each orbital before starting to pair them up. Because it wouldn't make sense to do this. If I grab this electron and I put it here, these 2 electrons are now too close together and they're repelling each other. Why would nature do that when there is a better choice? Because these orbitals all have the same energy, that third electron can easily go here, and these electrons can be divided up where they have a lot less repulsion. They don't want to be in the same orbital, if there's a choice, anymore than you would want to share a room if there were enough room so everyone could get their own. All right. So this is the electron configuration for the phosphorus with its 15 electrons. Let me erase my arrows. And then it's going to be the same thing with iron. Iron has, let's bring up the periodic table. Oops. So iron has, according to the periodic table, we find Fe, which is here. Iron has 26 electrons. So it's 26 electrons. Again, we're going to do this a very similar way that we did before. We're going to grab our 26 electrons. Let me do this in a different color. We'll do it in, let's use green. So 26 electrons. Ooh, that's not very good. Let me use a different color. Also red. So we're going to have 26 electrons for iron. Again, the number of electrons in each sublevel is going to be, it's going to go by the same rules that we had before. So if we have 26 electrons, that's 2 in the 1s, 2 in the 2p, because that's the max they can hold, 6 in the 2p, because that's the maximum we can hold, 2 in the 3s, 6 in the 3p, 2 in the 4s, so that's 2, 4, 10, 12, 18, 20. So we have 6 electrons left in the D sublevel. Well, when we put those 6 electrons left in the d sublevel, again, we're going to fill this in from lowest to highest, 1 electron at a time, and when we have multiple orbitals in a sublevel, 1 electron each orbital before we start pairing them up. So this is going to be 1, 2 for the 2 in the 1s, 3, 4, the 2 in 2s, 5, 6, 7, notice how I'm putting 1 in each, 8, 9, 10 for the 16 2p, 11, 12, that's 3s, and 12, 13, 14, 15, 16, 17, 18, 3p, 19, 20 for 4s, and then the 6 that we put in the 3d. Again, we're not going to put 6 by putting 2 in the first 3. We're going to do 1 per box. 1, 2, 3, 4, 5. Now that we don't have anywhere to put the 6th one that's not already taken, that's when we put the 6th one paired up back in the first box. And again, always remember that if there's 2 in an orbital, if there's 2 in a box, they have to point in opposite directions. So these are the box notations. Now, normally we wouldn't obviously put all of them stacked up like this. So normally what I would do is if I wanted to do hydrogen, I would just put the 1s below it. That way, or on top or below the box. So if I went to do sodium, I would put 1s, 2s, 2p, 3s. If I wanted to do phosphorus, I would 1s, 2s, 2p, 3s, 3p, for the 1s for hydrogen. And then if I went to hydrogen here for iron, I would do 1s, 2s, 2p, 3s, 3p, 4s, 3. So they're just showing you multiple at a time, but normally we will write those sublevels below the boxes, the orbitals that they belong to. So, oops, let me erase my lines so you can see. So these are just the different box notations. So it's very similar to what we did with these 1s or the standard notation, but the main difference being that we are now adding some extra rules because we're showing that orbital level. Again, those extra rules being that each orbital, so we have the first rule, which is just from least energy to highest energy, same rule we had for the standard notation. Then we have the second rule, which is that the electrons, there can only be 2 per orbital and that they have to point in opposite directions. That's, again, special because we're now showing orbitals. And then the third one is that when we do electrons into orbitals that are in the same sublevel, like the 3p sublevels or the d sublevels, or orbitals in the d sublevels, that we have to put 1 in each orbital before we start pairing them up again, like we did here with iron and with phosphorus. All right. But that's how we do box notations for Cambridge. And you will be asked to this once in a while. Now, box notations do bring us some interesting things that we need to talk about. So we're going to go to that now. And the first interesting thing here is spin pair repulsion. Spin pair repulsion refers to the fact that why those electrons can be paired up until there's 1 in each orbital in a sublevel. So electrons in the same orbital obviously are going to repel each other. And we call this spin pair repulsion. Essentially, when we have 2 electrons in the same orbital, like the 1s here or the 2s here, those electrons are going to repel each other, and they really have no choice sometimes. Like with s sublevels and the s orbital, those electrons have to be in the same orbital. They have no choice. And so the spin pair repulsion is there, but it doesn't really make a difference. It's not something we have to consider because there's no alternative. However, once we get to the p sublevel, that's when, and or D or F, when they have orbitals in the same sublevel with the same energy, that's when we have starting alternatives. So spin pair repulsion is going to be something to consider. The reason why, when we have 3 orbitals in the same sublevel, so that is not the color I wanted. So the reason why when we have 3 orbitals, we draw them like this. Ooh, what happened there? We draw 3 orbitals. So I'm going to draw here the 2p's. So the reason why when I have 2 electrons, they go like this and not like this is spin pair repulsion. This on the top one is correct. This is not. Why? These are repelling each other. This is creating spin pair repulsion that's unnecessary. Why is it unnecessary? One of these electrons can easily move into the next orbital, which will allow them to not have spin pair repulsion. There is an alternative. And that's why this rule is there for box notation, because that's what naturally happens. So if we look at the electron configurations for carbon, for example, that's why in the p sublevel for carbon, we have the 2 electrons, and this is just a vertical version of the box notation instead of horizontal. We have the 2 electrons in the p sublevel being in different orbitals, because if they were in the same orbital, they will repel each other. It will create spin pair repulsion. Nitrogen, same thing. The 3 electrons in the 2p sublevel are in the 3 individual orbitals in the 2p. And that's because in this manner we avoid spin pair repulsion. These are not repelling each other because they're not in the same orbital. Once we get to oxygen, however, and we have 4 electrons in that p sublevel, and we can see that here, then because we have 4 electrons, spin pair repulsion is now unavoidable. Those 2 electrons in the first orbital need to be there because there's only 3 orbitals in the p sublevel. And so spin pair repulsion in certain situations, like in oxygen, is unavoidable. But if it can be avoided, like in nitrogen and carbon, then nature does avoid it. All right, and nature is going to put 1 electron in each orbital. And this actually plays a role later on. We'll talk about spin pair repulsion when it comes to the order of, or the reasons behind things like ionization energy and why there are certain exceptions to the trends that we see there. But for now, just remember, spin pair repulsion refers to 2 electrons in the same orbital repelling each other. And when nature can avoid this, it will, like it does in carbon and oxygen, in nitrogen, when there are more orbitals and we can spread those out. But sometimes, like with oxygen, we cannot because that 4th electron has to go into a p sublevel, and all 3 of the orbitals already have an electron in them. So that spin pair repulsion is going to be unavoidable. All right. Now, we talked about both standard and box notation for elements, and for ions, it's going to be very similar. We're still going to do electron configuration for ions. All you have to consider, though, is that you will have either more or less electrons, whether the ion is positive or negative. So there's no difference in the rules that we follow for electron configuration. The rules that we follow for electron configuration are going to be very similar to what we had with just regular atoms that don't have any electrons added or removed. But with ions, because we either lose electrons with positive ions, with cations, or we gain electrons with negative ions or anions, that's all we have to take into consideration, really. We're either going to have more or less electrons in the electron configuration. So let's look at, for example, sodium. The electron configuration for sodium down here sodium naturally has 11 electrons. So the electron configuration is 1s2, 2s2, 2p6, 3s1. Well, when we have the sodium plus 1 ion, that plus 1 means we have lost 1 electron. So instead of having 11 electrons, we have 10 electrons. Well, all we have to do is then grab this very last electron from 3s and remove it to get the electron configuration for the sodium ion. The difference between the sodium ion and the sodium atom's electron configurations is literally just the 1 electron that is lost. And that's because it's a cation, so we remove the electron. With an anion, like with sulfur, sulfur has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p4. So it has 16 electrons. When we have the sodium 2 minus ion, the anion of sodium, we have that 2 minus ion means that we have gained 2 electrons. So we have 18 electrons in total. Well, if we have 18 electrons, then the difference between the sodium ions and sodium atoms electron configuration is going to be 2 electrons. But because they're being added, because it's negative, we're going to add 2 electrons to the electron configuration of the sodium ion. And we always do that to the very last electron sublevel, energy sublevel. So the 3p4 now becomes 3p6. And most elements, most of the representative elements, will do this to completely fill out that sublevel at the end. So if they gain electrons, you're going to be completely filling in that sublevel. So we go from 3p4, which is partially filled, to 3p6, which is fully filled. Or if they're losing electrons, they're going to lose enough electrons to get rid of that sublevel at the end and become, again, fully filled. So we go from 3s1, we remove that electron in sodium. Now our last sublevel becomes 2p6, which is already fully filled. And this is going to be most representative elements. Now for the transition metals, that might be a little different. Because one of the things that we need to keep in track with the transition metals is that when transition metals lose electrons, those electrons come from the s orbital first. Meaning that we're going to lose s electrons first before we lose the d electrons from the d sublevel. So, for example, here we have iron. Iron has 26 electrons in total. So let's write that down. So we have iron with its 26 electrons. So the electron configuration for iron, as we discussed earlier, was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, right? Well, when we have the iron 2 plus ion, and all of the transition metals, because they're metals, are going to be positive, then we have lost 2 electrons, with iron 2 plus having 24 electrons. And that's where this is important. If we write it in the way that we normally write it, 4s2, 3d6, the electrons that we remove, those 2 electrons that we remove from iron to iron 2 plus, are actually going to be removed from the s sublevel. So notice how the electron configuration for iron 2 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So we're not touching the 3d sublevel. We're getting rid of the 4s sublevel electrons first. And that is always going to be the case. With transition metals, the electrons that we remove, because we're always removing their metals, come from the s orbital, not the d orbital. It is not until we are done with that s orbital that we move to the d orbital. So, for example, with iron 3 plus, we have 23 electrons. When we remove from iron to iron 3 plus those 3 electrons, we remove the 2 from the s sublevel, but then we need to remove 1 more. The only place left for us to remove it from is then that d sublevel. So we're going to remove the 2 from the s, because again, from here, from iron to iron 3 plus, we're removing 3 electrons. We're going to remove the 2 from the s sublevel, because they always come first, and then we're going to remove 1 from that d sublevel to go from d6 to d5. So this is very tricky. You have to remember that transition metals were always removing s sublevel electrons before we remove the sublevel electrons when we form their ions. But other than that, ion formation is really just the removal of those electrons if it's positive, or the addition of those electrons if it's negative. All right, so keep that in mind. All right, so let's look at a sample question from paper 1 that goes along with this idea of doing the electron configuration for an ion. So if we go to the next slide, if we look at this question is paper 1, and it's a normal multiple choice question, but you'll notice that it's actually a bit of a high level of critical thinking because we're not working with a specific element. There are things we have an ion X plus 1. Well, a few things to notice. If it's plus 1, that means we have removed 1 electron. So that's something I need to take into account. The fact that we remove 1 electron, let me make this a little better. We have removed 1 electron from the original atom because of plus 1. Again, we don't know what the original atom is. It's just X is a placeholder. And they tell us that this ion contains 8 protons. Now, this gives us more information than we would normally think. Because an ion having 8 protons means that originally, the original atom had 8 electrons. And this is where the critical thinking comes in. If we have 8 protons in the ion, that means the original atom had 8 electrons. But we have removed 1 electron because it's a plus 1 ion. That means that X plus 1 has 8 electrons originally, minus the ones that we remove, has 7 electrons in it. And that's where the critical thinking comes in. You have to be able to think logically through a series of steps. We have 8 protons, so the original atom had 8 electrons. And because it's a plus 1 ion, that means that we remove 1 electron. So instead of 8 electrons, we have 7 electrons. Well, from there, we can actually go through these without even actually doing the electron configuration and looking at which of these have 7 electrons, because anyone that don't are not going to be the answer. So if we look at A, we have 6, 7, 8, 9. So that's not the answer. We have B, 3, 4, 5, 6, 7. So B could be the answer. 5, 6, 7, 8, 9. So that's not the answer. And then D has 7, 8, 9, 10, 11. So that's not the answer. So the answer, just by knowing this, and we could go into, okay, it has 7, so it's 1s2, 2s2, 2p3, and which is what B is. But without even actually having to do the electron configuration, by using the answer choices, which is a very important technique that you need to start mastering for paper 1, to use the answer choices to help you. We can tell that the answer here is going to have to be B, because it's the only answer with 7 electrons. So again, without actually ever doing the electron configuration, we can tell that right away. We could also have right away eliminated A, because even though A, even without knowing that it needs 7 electrons, A has 1s2, 2s1, 2p6, so that is wrong because this 2s needs to be fully filled before moving to 2p6. So we could have eliminated that. We could have eliminated D without even looking at the number of electrons, because D has 2p7 and this p sublevel cannot hold 7 electrons. So even by just looking at what the rules of electron configuration was, we could have narrowed this down between B and C. But by actually using critical thinking and realizing that this has to have 7 electrons, we know that the only possible answer is B. So that's the electron configuration for the ions of the elements. We're going to look at one more thing, and that's because sometimes when you do electron configuration, or when you do ions and you remove electrons or add electrons, you end up with something that we will need to discuss much more in depth when we do organic chemistry, but we're going to introduce right now. And that's the idea of a free radical. A free radical is a species, whether it's a compound or a single atom, that has an odd number of electrons, meaning that has an unpaired electron in its valence shell. Groups of atoms can be free radicals, or single atoms could be free radicals. So, for example, if we look at the atom of chlorine, which is the first radical we're going to look at, the atom of chlorine by itself, not the chlorine molecule, which is Cl2, not the ion of chlorine, which is Cl-, but the atom of chlorine, the neutral atom, has 7 valence electrons. So when we do the dot structure for it, it looks like this. We have Cl with 1, 2, 3, 4, 5, 6, 7 valence electrons. Again, this is only showing the outer shell of chlorine on the valence electrons, but that means that because the inner shells either have 8 or 2 electrons, this has an odd number of electrons because this 1 electron is not paired up. That makes the atom of chlorine a free radical. This other molecule, the CH3 molecule, is also a free radical. We have carbon bonded to 3 hydrogens, and then 1 electron on that carbon is by itself. Well, that makes this CH3 molecule a free radical. Now, free radicals are extremely reactive. As we know, electrons usually want to be in a stable conformation, and having an odd number of electrons like this, where one of the electrons is not paired up, makes those atoms, those free radicals, extremely reactive. So whether it's chlorine, which doesn't exist in nature by itself, or the CH3, which also doesn't exist in nature by itself, they don't exist in nature because they're so reactive, they'll pair up or they'll attack anything they see. And this is going to be an important point to study when we get to organic chemistry in chapter 14. But until then, just know the definition. Free radicals are a species with one or sometimes more than one unpaired electrons. Also sometimes defined as being a species with an odd number of electrons, meaning that one of them will be unpaired. All right? So know the definition of free radicals for now, and then when we get to organic chemistry later in the year, we'll actually delve into what they do. That is it for section 4 of chapter 2. We'll see you next time for section 5.